flow of consciousness type things. How's everyone doing? Good. I'm doing okay. Thank you for asking. It's good to have someone to talk to, you know. Good mental health. Sorry, what?
Is your grading done?
No. I still have to grade your guys' midterms. You know, you want to know.
Well, I forgot about that.
Well, you forgot about that because you're all going to pass the class. So there's a reason that you forgot about that. Oh, I don't need to know. I'm passing the class anyways. And we got to start having our powwows. I got to meet with everyone sometime in the next week and a half or so. But more about that later. But now to the important things. Today is February 27th, and I've heard that there is something historical about this date. Someone was telling me in the elevator.
Indeed there is.
Indeed there is something historical.
It's a big day.
What happened on this day?
We were graced with the presence of a great man.
Wow. But you're wrong, my birthday's not till May. Wait, but maybe there's a second one.
Yeah, the second greatest, I suppose.
Okay, all right. Well, should we do anything to mark this occasion?
Yes.
Sing. Totally sing.
We should sing, okay. All right. Is there someone who's willing to lead us in song?
You are a great leader.
One of the things that makes me a great leader is encouraging the next generation to get up and take over their managerial and leadership roles. So, Beth, would you like to be the one
I
to?
would like to nominate Adam.
Me?
Yep.
You want to do a duet? Oh, yeah, we got this.
No.
Well, you're leading.
We're leading
right.
right. Also, it's Alex's birthday.
Yes.
You worked away.
Oh. So Alex Schulte, congratulations. And okay.
1, 2.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Alex. Happy birthday to you. Yeah. And my apologies to everyone who just had to listen to me sing on YouTube. Okay. All right. Well, anyways, moving on. So Alex, can you now drink? Are you of drinking age?
Not quite. Next year.
All right. There's always the hope. All right.
I can rent a car.
Good. Well, that's a good sign, you know.
2 years ago, as well.
So. All right. So last time I started by talking about Courant-Fischer theorem, and of course I messed up, and so this time I prepared. So Courant-Fischer theorem says what? Well, says suppose you have a real symmetric matrix, so now we know it has real eigenvalues, and they're ordered. Lambda 1 is at least lambda 2, is at least lambda 3, so forth and so on up to lambda n. And some notation here. So a capital X with the exponent k just refers to any k-dimensional subspace. So I'm assuming I'm over Rn, so I have a k-dimensional subspace of Rn. And the X with this symbol here that I read that as perp. In LaTeX, that's /perp of x to the k. That just says I'm perpendicular to that subspace. So x is perpendicular to everything in that k-dimensional subspace. So now with that notation, we can say the following. If I want to find lambda I, the ith largest eigenvalue, I can do it in one of two ways. One way is I can take the minimum over all possible I minus 1 dimensional subspaces, and then for a fixed I minus 1 dimensional subspace, what I'm doing is I'm taking the maximum of x perpendicular to that I minus 1 subspace, and as long as it's not 0, because the 0 vector is bad, of the Rayleigh quotient x transpose mx over x transpose x. So I'm taking again, I'm taking a min of a max. Where the min I'm running over subspaces of a certain dimension, and the max I'm saying, well, what's the largest possible Rayleigh quotient you can get? I can also do max of a min, and the only thing that changes, well, is the size of your subspace. So max is an n minus I dimensional subspace, and we say, well, let's just be perpendicular to that when we take our min. Now, the way that you should interpret all of this happening here is what's going on. Well, what you want to note here is, well, what are these ideal subspaces? So in other words, if I wanted to say what actually minimizes this expression, because I said lambda I is a min over these I minus 1 dimensional subspaces, and the answer here, let's see. Boy, I wrote this down and I was 100% sure it was right. And now when I come to explain it, is this right, Beth? I'm sure this is right. It's got to be right. Yeah, it's got to be right.
I believe you.
Thank you. I believe me too. So what's happening here is where's the min? Is you're taking x1, x2, up to x sub I minus 1, where these are the eigenvectors for the first I minus 1 eigenvalues. That's how this works. Now, if that's my particular dimensional subspace, so x1, x2 up to xi minus 1, so if that's my I minus 1 dimensional subspace, and I'm saying, well, how large can this be? Well, the answer is, the ideal thing is to pick xi, your eigenvector for the ith eigenvalue, because that will give you this ratio of lambda I, and you can't do better. You can't do better. Now, if you pick any other subspace besides this, then you can say, aha, what will happen is you can do an intersection. You can say, well, what I'll do is I'll find something which intersects with the span of this I minus 1 dimensional subspace. Because if anything which intersects with the span of this I minus 1 dimensional subspace, you can show has size at least lambda I minus 1. So you can capture a little bit of that. So anyways, this is the same philosophy down here, where when we talk about the max, then in that case, we say, what's the ideal thing to do? Well, it is start with the I plus 1 up to xn. And then you say, okay, that is going to be the eigenvectors for the last n minus I minus 1. Or let me see, did I get that right? No, n minus I. That's last n minus I eigenvectors. And you say, well, how can I make this as small as possible? Well, the answer is choose the ith eigenvector. So this is how these things work. Now, most of the time, we don't actually use Courant-Fischer in this form, because we focus our energy on a few special cases. So the special cases that we almost always focus on are what happens with the largest eigenvalue and what happens with the second largest eigenvalue. So there's a few special cases. So for instance, lambda 1, we can say that in the following way. If I come back into this previous slide, I'll just point out for lambda 1, that's I equals 1. So I can point to this first one where I'm taking a min over zero-dimensional subspaces. Well, how many zero-dimensional subspaces are there? There's one zero-dimensional subspace, which is the zero vector. The zero vector is a zero-dimensional subspace. So it's actually a very easy min, and therefore it's the max of everything that's perpendicular to the zero vector, which of course is everything is perpendicular to the zero vector. So we get the following. Lambda 1 is equal to the max over all non-zero x of x transpose mx over x transpose x. Okay, let's just do a quick application of that. We'll make it fairly simple and straightforward. So here's an application. Suppose I want to say something about lambda 1. So here's a basic fact. Lambda 1 is greater than or equal to the average degree. Okay, so that's a claim. I'm saying lambda 1 is at least the average degree. Now, how can we prove it? Well, here's a proof. Notice that lambda 1 is the max over all possible x. Okay. Oh, I apologize. People are looking at me in a very strange way. I haven't specified which matrix I'm using. This is for adjacency. Now people can okay, now it makes more sense. Okay, so when I'm looking at lambda 1, I'm taking a max over all possible vectors, and I say, okay, let's be smart. Let's choose an interesting vector. Well, what's an interesting vector? The all-ones vector is amazingly interesting. It's perhaps the most interesting vector in spectral graph theory. And you will say to yourself, can there possibly be a more interesting vector? And the answer is no. It is the most interesting of vectors. So there's a simple observation to say, well, look, I'm taking the max. Well, certainly that's greater than or equal to any one particular value. So I'm going to take the all-ones vector transposed, and I sort of put A there. A all-ones vector over all-ones vectors transposed times the all-ones vector. Now, downstairs, it's pretty simple. If I take the all-ones vector transposed times the all-ones vector, what do I get? I get n. I get how many entries I have. Now, upstairs, a little bit more interesting, what do I get? You do get the sum of the degrees. Now, do you know that because I already stated that that my result is the average degree, or?
You're going to add up.
Yeah.
Thank
So,
you,
so, Seth was doing the our interpretive dance routine here. So A1, when I multiply A by 1, that produces a vector, and that vector has the degrees. And then 1 transpose times that will add up the degrees. So that's the sum of all your degrees. Well, sum of your degrees over n, that is your average degree, which some people might denote by a d bar. I don't know why bar has been chosen to represent average, but it's a fairly common thing, so I'll stick with it. Yeah, but I don't know why they chose it. You know, why did the statistician say, let's put a bar on top of it? I don't know. Okay, so there's one application. Now, is this good? Well, in some cases it's good, in the sense that there are some graphs where it's true that lambda 1 is in fact the average degree. Can we give an example of a graph where lambda 1 is equal to the average degree? Or perhaps infinitely many graphs? A regular graph, absolutely. So if a graph is regular, all vertices have the same degree, and it turns out that that value is the same as the eigenvalue lambda 1. Now, for most graphs, this is not the case. We can do a little bit better. On a side note, that's a lower bound. I don't think we've given an explicit upper bound for lambda 1, so let's just go ahead and just throw one out there. Lambda 1 is less than or equal to the max degree.
Before we get too far, I wanted to ask you
Sure.
A classification of regular graphs if lambda 1 is your max degree. Like,
Yes.
okay, so it is a classification. Like going back and forth. Right?
Well, max degree or average degree. Hold on, I should step back. Lambda 1 is max degree or lambda 1 is average degree? Yes, if lambda 1 is your average degree, then you are regular. Yes. Yes. And in fact, I should say, and I haven't said this out loud, but I think it's been implicit in the book, which apparently almost everybody has read the book except me. Because people keep telling me about how great the book has this reference here and this reference there. I'm like, wow, I should read it sometime. That sounds like a great book. But one of the things that is stated, and I think this is in the first chapter. I have read parts of it. I don't want to. That if it's the case where if the graph has the all ones eigenvector, then it has to be regular. But in fact, it's also the case that if your average degree is indeed your eigenvalue, and it has to be lambda 1, then the graph has to be regular. And so you can tell if a graph is regular based off of the adjacency matrix and also off the Laplacian and off of the silence Laplacian. All those will tell you if a graph is regular. I will warn you, there are certain matrices where you can't tell if a graph is regular just based off of the spectrum. Any guesses? Yeah, the normalized Laplacian, you can't tell if a graph is regular. Well, how do we know that? Well, proof by example. If I take the graph K22, also known as the 4 cycle, and the graph K13, it's easy to see that the 4 cycle is regular of degree 2, but K13 is not regular of any degree, but they're co-spectral because they're both complete bipartite graphs. Okay, lambda 1 less than or equal to max degree. All right. We have a nice proof for this that we've mentioned, a tool that we can use that just gives it to us automatically. Without any work. Okay, good. Proof by design theory. I like that. Okay. QED. Also, you can use Gershgorn disk theorem. Also, you can just notice that lambda 1 is, by Courant-Fischer, what we would call the, I'm trying to remember, is it infinity norm or 1 norm with the row sums? I can't ever recall which one is which. Right. That's right. Well, it doesn't matter. Lambda 1 is less than or equal to the infinity norm, and lambda 1 is less than or equal to the 1 norm, and it doesn't matter which one of these you use. Either the infinity norm or the 1 norm, they're the same for our symmetric matrix.
Ah, yes.
They're both equal to
I think one is columns and
max
one is
degree.
rows.
Yes. Yes, one is columns and one is rows.
is an infinity.
That's right.
Yeah.
Is one go straight up and down? That'd be a nice way to remember it.
I think it's 1.
I want that to be true just because it looks cool when you do it like that. So for those of you who can't see Beth on my little tiny projector here, she went 1 to infinity. So it's like the straight up and down. Whether it's true or not, I want to believe it's true. I want to believe. Okay, so that's lambda 1. Well, lambda 1, most of the time people work with regular graphs and they're like, okay, we know lambda 1, we know what it is. Lambda 2, that's where the action's at. That's where things get exciting. So, pulling this back up, what can we say about lambda 2? Well, lambda 2, that's I equals 2. So that's the minimum over all one-dimensional subspaces of the max being perpendicular to that one-dimensional subspace x transpose mx over x transpose x. But look, we know what that one-dimensional subspace is. What is that one-dimensional subspace that will achieve this min? I'm not asking for an explicit vector. I'm just saying the vector that does this such and such is that one-dimensional. Yes, that is correct. So it's the eigenvector corresponding to the largest eigenvalue. So lambda 2, we now can say it's the following. It's the max over all x, where x is not 0, and x is perpendicular. And I apologize for using x for so many symbols here, but I'll just have to go with it. X sub 1? No? You don't like that? Okay.
That's a little x1.
It's little x1. Okay, apparently we're back on track. Beth has approved. So remember that this little x1, which is terribly written here, this is the eigenvector for lambda 1. So I'm perpendicular to that eigenspace generated by that small first eigenvector of x transpose mx over x transpose x. Now, what can we do with this? Well, let's do another application. So, here we go. Application. And again, I'm going to focus on the adjacency matrix for right now. All right, claim if G is not the complete graph, then lambda 2 is not negative. Now you might remember that if you are the complete graph, your eigenvalues are very nice. They are n minus 1 is your largest eigenvalue. And then what happens is that you get -1, -1, -1, so forth and so on. And so that your second eigenvalue is actually negative. Now, I am claiming that, look, if your second eigenvalue is negative, that's in fact a characterization. There's only one graph that has that. In every other graph, the second largest eigenvalue at worst is 0. Now, there are graphs where the second eigenvalue is indeed 0. And let's just, to avoid trivialities, and people would say, oh, yeah, take the empty graph on n vertices. Okay, let's assume a graph is connected. Can anyone come up with an example of a connected graph where the second eigenvalue is 0?
The complete bipartite graph.
Yeah, the complete bipartite graphs are examples of this. So it's possible. So you can't do better than this. Okay, well, what do I need to do? I somehow have to argue that I can bound this ratio x transpose mx over x transpose x, where m is the adjacency matrix, where I'm taking a non-zero vector which is perpendicular to x1. And at the same time, for added difficulty, I have to somehow use the assumption that G is not complete. All right, so let's start with that assumption, G is not complete. If I know G is not complete, what must be true?
There exists a 0 off the diagonal.
Yes, that must be true. But there must exist a 0 off the diagonal, but phrased in terms of graphiness, not matrixiness. How would you say that?
There's an edge in the complement.
There's an edge missing. There's an edge that's not there. Edge in the complement, as Beth has said. So, okay, so there exists a pair U, V, where U is not adjacent to V. Okay. So that is, in fact, as much as I can say, given that I know G is not complete. I can't go any further than that. And I might not want to, because that's as far as I need to go. Now, what do I have? Well, I have that my vector x1, this vector is the vector for the largest eigenvalue. What can I say? What's true? Doom, 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 doom. Using? Doom. Courant-Frobenius. Okay, so using Courant-Frobenius, the vector is positive. For me, the key thing about that is really to say, I know that there aren't any 0 entries there. And I'm going to use that because I need to make sure I'm constructing a non-zero vector. So I know that x1 of u and x1 of v are non-zero. Okay, so I found 2 vertices, and I happen to know that if I look at x1 at u, the principal eigenvector for the largest eigenvalue, that's non-zero. Look for v, that's non-zero. Now, here's what I'm going to do. I'm going to construct a matrix y. And y of a vertex x is one of 3 things. It's 0 if I'm not u or v. And it's going to be x1 of u if what? Can you figure out what goes next? Oh, this is the fun part. Read the professor's mind. What is he going to put next? Ooh, that's a good guess. Yes! All right. Participation points. That's important in this class. And minus x1 of v if x is u. Now, you might wonder, why did I choose it to do it this way? Well, oh, wow, I've chosen really terrible notation here. Because I'm now using x like in 4 different ways on the same slide, which is like a really terrible thing to do. You should never follow that example. Never repeat what I just did. always introduce new letters, even if you have to make letters up. Okay. Okay, what I claim is two things. Claim number one is that if I take x1 transpose times y, what will I get? I'll get 0. Very good. And why? Well, because most of the entries of y are 0, except for the one corresponding to v and the one corresponding to u. So I'll get x1 times v times x1u, and then I'm going to get minus x1 of u times x1v, which they cancel out, so I get 0. Okay. So, moral here is, lo and behold, x1 and y are perpendicular, which is good, because when I'm looking at lambda 2, I need to take something which is perpendicular to the first one. So what's left? Well, let's compute y transposed ay over y transpose y. The other thing I should have pointed out is, of course, we've already said it's the non-zero vector. But y transposed ay, whenever you're doing something, y transpose ay for the adjacency matrix, this is equal to sum over all edges u adjacent to v of 2 times y sub u, y sub v over y transposed y, which is magnitude of y squared. But here's the question. What's true about the sum upstairs? And again, I chose terrible notation. U and v are fixed, and now it's 0. Why? Well, because anytime I have an edge, one of those two terms is 0. Because the only time that both terms are non-zero is precisely when there's not an edge. And therefore, the claim is true. This is indeed 0. And, well, remember lambda 2 is the max, so we just found one y vector. So this is definitely the max of this is greater than or equal to what happens when I take the y vector, and therefore lambda 2 is greater than or equal to 0. Okay. Phew. Good. All right. Well, that was easy.